Good morning, friends. Indeed, I am very much privileged to be here again for my favorite course on engineering thermodynamics. And in my previous lectures, we have discussed about the heat transfer, effect of aerodynamic forces on falling raindrop, and how the work is done. Also, we have solved the problem of piston and the cylinder when the piston is not part of the system, and when we take piston is also part of the system, what the effect going to be there. And we have seen that in our problem number 2 that if the piston is not part of the system, the weight of the piston will also be considered, and if piston is part of the system, the weight will not be considered because it is inside. The effect of weight will not be felt in the system. But we have seen that the heat transfer will remain same because it is the insulated. So for any system, it was the same. And also we have seen the direction of the flow of energy, or the flow from A to B or B to A. So in which direction, if we take the entropy, if the entropy is coming negative, it means the flow which we have assumed in the previous, you remember that we have seen that from this is A side and this is the B side, we got that from A to B, delta S we got negative. So if we get the delta S negative, means the flow is not from A to B but from B to A, because this will be always positive. So if you lose, it will become the positive. So this we have seen with the help of the numerical that this process is the process was not possible from A to B, but it was very much possible from B to A. In this way, we have seen in our previous lecture. In today's class, we are going to discuss about some numericals again. And numerical number 1 about Carnot cycle efficiency calculations. Numerical 2, Carnot cycle source temperature calculation. Numerical 3, reversible cycle heat transfer calculation. Numerical 4, refrigerator coefficient of performance calculation. These are the, so here we have the Carnot cycle and we have the for engine and Carnot cycle for the refrigerator. And we will see that how these things are varying, and very interesting thoughts will be coming up in this lecture. Hope you will enjoy and be tuned for this lecture. So this is a numerical number 1. We will see that an engine work on Carnot cycle, it rejects 30% of heat it absorbs from the source. The sink is at 25 degrees centigrade. Calculate the source temperature and the maximum efficiency. Okay, so it is very interesting. So this is the source and this is the sink here. So the engine works, so there is an engine. So normally it is the engine, so it will go like this and work will be produced. So engine works on a Carnot cycle. It is the most efficient engine which we can produce is the Carnot cycle, and 30% of heat is absorbed from the source. So from here 30% is absorbed, and the sink temperature is 25 degrees centigrade. 30% is absorbed, so 70% is rejected. So means this QL and W is equal to this is the QH. So this we have to see that calculate the source temperature and the maximum efficiency, being this is the, we will assume as a Carnot cycle. So here first we will see the diagram again. Here that this is the source. From the source we have to, okay, this is the taking the heat from the source, that is called the QH, and this is here engine. This engine is QL and this is given as a 25 degree centigrade. So for the Carnot cycle, we can write that QL by QH is equal to TL by TH. So given QL is equal to 30% of the QH. So QH is equal to 0.30 of QH. So TL is equal to 25 degrees centigrade plus 273. So you will get 290 Kelvin. TL is given. So we can see that QL by QH here. So here we can see that QL by QH is equal to 0.3. It is given. So QL by QH is equal to 0.3 is equal to 298 divided by TH. So this TH is equal to 298 by 0.3. We will get 993.3 Kelvin or 993.3 minus 273. So you will get 0.3, 0, 2 and 7 degrees centigrade. So you get 720.3 degrees centigrade. So this much, this temperature, the source temperature is 993.3 Kelvin or 720.3 degrees centigrade. So this is the temperature of the source. So it is asking the question, what is the temperature of the source? So in this way, we can find out the temperature of the source. Now efficiency of the Carnot cycle is equal to 1 minus QL by QH. QL by QH is equal to 0.3. So efficiency is 0.7 or 70%. So this is the most or highest efficiency which we can get by the range of temperature TH and the lower temperature is TL. So by the 720.3 degrees centigrade, the high temperature TH and the lower temperature is 25 degrees centigrade, the maximum efficiency we can get up to 70% only. So that is the Carnot cycle which explains the maximum efficiency. So we have got by this help of the highest temperature of the source which is supplying the heat to the engine and the lowest sink, and the efficiency of this engine we got is 70%. Now we will see the numerical number 2. In that we have a heat engine operates between a hot reservoir at 500 Kelvin and the cold reservoir at 300 Kelvin. It absorbs 3500 joule and rejects 2500 joule of heat. Calculate the work done, efficiency and the maximum possible efficiency by this system. So here we have got the TH, that is a high, that is a reservoir, the source temperature is 500 Kelvin and the TL or the sink temperature is 300 Kelvin. It absorbs 3500 joules and rejects QH and QL is also given. TH, TL, QH, QL. Calculate the work done. So we have to find out the work done. How much is the work done? So if you see here, this is the sink, this is the source, this is the 500 Kelvin, this is the TH, TL is equal to 300 Kelvin from here. This is the QL which is given as a 2500 joule and this is the QH 3500 joule and the work done. We have to find out how much work done first case. So we have to work done by this system, then efficiency eta of this system and maximum possible efficiency and eta maximum. So how much is there? These things we have to find out by the help of the Carnot cycle or the Carnot principle. So here we can see that given TH is equal to 500 Kelvin, TH here is equal to 500 Kelvin, this is 500 Kelvin, TL is equal to 300 Kelvin, QH is equal to 3500 Joule, QL is equal to 2500 Joule. So heat engine, for this heat engine, what is the work done? Eta and the maximum efficiency. So applying the first law of thermodynamics, we can see that the cyclic integration of del Q is equal to cyclic integration of del W, or the sigma del Q is equal to sigma del W. So QH plus QL is equal to W. So here we can write that QH minus QL, because if you see for this it is entering and this is the leaving. So this is the positive QH and this is the entering, so it is a minus. So QH minus QL is equal to W. So 3500 minus 2500 is equal to 1000 Joule, or this is the work done. So this is the work done. That is the first answer. We got the 1000 Joule or 1 kilo Joule. That is the work done. Directly, very simple. We have got this, but we should know the concept how we should start the process. Now we have to find out the efficiency of the system is equal to the net work done divided by QH. So net work done is QH minus QL by QH. So this QH is equal to 1 minus QL by QH. So we can see that here that this QH minus QL is equal to 1000 and QH is equal to 3500. This. So here 2, here is the 7. So here we will get 0.2857. This is the 28.58% of efficiency we got it. So this is the efficiency for the given condition. But how to find out the maximum efficiency? Okay, so now find out the maximum possible efficiency for the reversible engine is between the given the temperature TH and the TL. So this maximum efficiency is equal to W by QH. So QH minus QL by QH is equal to 1 minus QL by QH, 1 minus TL by TH. So 1 minus 300 divided by 500. So 1 minus 3 by 5. So you will get 0.4 or 40%. So maximum efficiency is 40%, but the actual efficiency we got 28.57. So that is the difference. So engine, the actual efficiency is 28.5, but the ideal efficiency is 40%. And so here we can see the TH for the Carnot cycle is QH. This is a reversible heat engine, and here is a W, QL, TL. So delta W is equal to delta Q. So W is equal to QH plus QL. So we have got it that the efficiency of the maximum efficiency will be always within the 1 minus TL by TH, but the actual work done is equal to 1 minus QL by QH. That we have to take care of. And so for taking the work done, temperature is not important, heat is the important. But for the Carnot cycle, the temperature by the given range of TH means high temperature and the low temperature we have to consider. And in this, the Carnot cycle is used for this purpose. Now I will go for the numerical problem number 3. So in the previous example, we have seen that how the maximum efficiency and the working efficiency or the net efficiency matters. If you want to find out the net efficiency, you have to take the heat absorbed and heat rejected. But if you want to take the maximum efficiency, then you have to use the Carnot cycle, and in the Carnot cycle, your high temperature and the low temperature are very important. So in the for eta maximum or eta maximum is equal to 1 minus TL by TH, where TL is the lowest temperature and the TH is the highest temperature of the given system. That we have to take care of. Don't just confuse that both are same. Both will not be same. It is not possible to have the maximum efficiency of any engine like a Carnot cycle. So if you are getting more than the Carnot cycle or very near to the Carnot cycle, it means there is some problem, you have done some calculation wrong or something you have missed. Then only you will get the equal or more than the Carnot cycle. So again you revisit, rethink, and then you redo the work, then only it is possible. So I am going for my numerical number 3. A reversible heat engine operates between two systems at constant temperature of 600 degrees centigrade and 40 degrees centigrade. The engine drives a reversible refrigerator which operates between system at a constant temperature of 40 degrees centigrade and minus 20 degrees centigrade. The heat transfer to the engine is 2000 kilojoule and the net work output of the combined engine refrigerator is 350 kilojoule. Evaluate the heat transfer involving the refrigerator. Very, very interesting. So, first two things we have seen that they are the engines, and now it is a combination of engine and the refrigerator. Very interesting. So, in this we have to take a refrigerator, a reversible heat engine operates between two systems at constant temperature of 600 degrees centigrade and 40 degrees centigrade. So, two temperatures are there, okay, 600 and the 40 degrees centigrade. The engine drives a reversible refrigerator which operates between systems at constant temperature of 40 degrees centigrade and minus 20 degrees centigrade. The heat transfer to the engine is 2000 kilojoule and the net work output of the combined engine and refrigerator is 350 kilojoule. Evaluate the heat transfer involving the refrigerator. So, very interesting. It is a combination of engine and refrigerator. So, this you can see here that I have drawn here this diagram. So, it is given that TH of the engine is 600 degrees centigrade plus 273. You have the 873. So, here 873, it is a source. This source is giving heat to the engine. This is the QH. From this heat engine, work output is 350 kilojoule. And from here, QL, and the heat sink, it is rejecting at 313 Kelvin, means 40 degrees centigrade. So 40 plus 273, 313 kilojoule. It is a heat engine. It is a reversible heat engine. Now, if you see here that from here, it is minus 20 degrees centigrade. So it is 253. It is a 20. So 253, and it is here QL. Okay, and this is the refrigerator, and this is giving heat to the sink at high temperature. So these things are given here. So here engine temperature, the high temperature and the low temperature is given. For the refrigerator, TRL, low is a minus 20, this is the TRL, and THL is given. QH is equal to 2000 kilojoule, and so QH is given here 2000 kilojoule, and net work done is 350 kilojoule. So these parameters are given. So we have to start with efficiency. Eta is equal to 1 minus QL by QH. For the Carnot cycle, we can write 1 minus TL by TH. So here QL by QH is equal to TL by TH. So QL is equal to QH. So here QL is equal to QH into TL by TH. So QH is equal to 2000. It is given here. QH 2000 into 313 by 873. You will get 717 kilojoule. So QH is equal to QL. This we got as 717 kilojoule. This we got QL. Now if we apply the first law of thermodynamics, so this summation of del W is equal to del Q. So this del Q is equal to QH plus QL. So we can write here QH minus QL. So this W is equal to 2000 kilojoule. QH is equal to 2000 and minus 717. So you will get that here 1283 kilojoule. This is the work of heat engine. This is the work of heat engine. So work of the refrigerator is how much? Is equal to this work minus 350. Okay, so 1283 minus 350, 933 kilojoule work is required here. So this is the 933 kilojoule of work is required for the refrigerator. Now, for the refrigerator, if you see, for the engine we have done, for the refrigerator, delta Q, sigma Q is equal to sigma W for the refrigerator. So for Q, we can write QRH plus QRL is equal to WR. Need proper sign convention. So this W plus QRL, WR plus QRL is equal to WRH. So this WR is equal to QRH minus QRL. So W we got 933 is equal to QRH minus QRL. So we can see that for the reversible refrigeration, QRH by QRL is equal to TRH by TRL, 313 by 253, 1.24. So here we can write that QRH is equal to 1.24 QRL minus QRL. So you will get here QRL 1.24 minus 1. So QRH is equal to, you will get 1.2. So you will get QRL is equal to 933 by 0.25, 48205 kilojoule. So for refrigerator, we need 4820.5 kilojoule. That is the heat is required to drive the refrigerator. So we will see the next problem. So in this very interesting, we have got this, that we need this much heat, 4820.5 kilojoule for the, this much heat has to be rejected to make the minus 20 degrees centigrade of temperature. A very huge amount of heat has to be rejected by the refrigerator. Now I will go for the next numerical number 4. The food compartment of a refrigerator shown in the figure is maintained at 4 degrees centigrade. The food compartment of a refrigerator shown in figure is maintained at 4 degrees centigrade by removing heat from it at a rate of 360 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatt, calculate A, the coefficient of performance of the refrigerator, and B, the rate of heat rejection to the room that houses the refrigerator. So here the food compartment, here is the food compartment shown in figure, is maintained at 4 degrees centigrade. So this is the 4 degrees centigrade which we have to maintain here, 4 degrees centigrade, by the removing heat at the rate of 360. So this going at a 360 kilojoule per minute. If the required power input to the refrigerator is 2 kilowatts, so here it is a 2 kilowatt. So determine the coefficient of the performance of the refrigerator. So what is the coefficient of the performance of the refrigerator? The rate of heat rejection to the room, that house, and this we have to find out. So COP, what is the COP, and QH, rate of QH. These two things we have to calculate. So we can see here that solution, that the power consumption of the refrigerator is given, the COP and the rate of heat rejection are to be determined. So this COP and the heat rejection has to be determined. The coefficient of the performance of the refrigerator, we have seen the equation that coefficient of the performance is equal to Q dot L by W net. So Q dot is given 360 kilojoule per minute divided by 2 kilowatt. So 1 kilowatt divided by 60 kilojoule. So you will get here 3. So COP, you got the COP is equal to 3. So here, so this thing is always that this divided by this COP. So if you want the COP, it is always the QL which is required effect, and how much you give, that is the W net in. This is the COP of the refrigerator. So just directly you just put the value and transfer this thing, change it, you will get that 360 divided by, so you will get the 3 answer. Now if you see that is the 3 kilojoule of heat is removed from the refrigerator space for each of work supplied. So means, what is the meaning of this? Means 3 kilojoule of heat is required for every joule of work. Heat is removed from the refrigerator for each of work supplied. So this COP of 3 means for each kilojoule, if you supply 3 times, the heat will be removed. Okay, that is the meaning of the COP. Now the second part is the rate at which heat is rejected to the room that houses the refrigerator is determined from the conservation of energy relation of cyclic devices. So here we can see that Q dot H, this H is equal to Q dot L plus W in. So Q dot L is equal to 360 kilojoule per minute plus 2 kilowatt into 60 kilojoule per minute divided by 1. So you will get 480 kilojoule per minute. So the value of QH, the rate at which heat is rejected, is 480 kilojoule per minute. That we have to understand. This demonstrates that energy can change from one form to another form. So energy is same, but this work is also added and the 360 also added. Both if you add it, you will get the QH. That much heat is rejected from your food compartment. So that is the meaning of this system. So if you see the next topic, we can say that the numerical one, that is about the entropy changes in lake. Numerical 2, changes in entropy of systems and the universe. Numerical 3, direction of heat transfer. These are the references that is I have taken from this Yunus Senegal, Michael A. Bors, Thermodynamics and Engineering Approach, Tata McGraw Hill's 7th edition. Then NPTEL lecture from Professor Mishra, IIT Kanpur, Department of Aeronautical Engineering. From there I have taken. You are always welcome to ask any questions, and these are the any questions, and you can mail me to ydvedi@gmail.com. I also request you to subscribe this channel, like this channel, and give the comment in the comment box, or you can send the message or mail to my this ydvedi@gmail.com. Hope this lecture you might have liked very much, and you know that my next topic also I have told you just before. These are my next lecture topic. So this I will be discussing in my next lecture. Hope the present lecture you like it, and next lecture also you will like it very much, and we will see you soon. Do like, do discuss, do interact with me. Thank you very much for the joining. Good, best of luck, and thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.